Welcome to class. Next up, in our quest for tools to analyze dynamical systems, we're going to take a look at phase portraits. Before we can get to phase portraits, we need a little bit of vocab first. So when I have an ODE written as y prime equals f of xy, we call an isocline for that system any set of points where the slope is the same. Right? So if I have some constant c, and you can just choose whichever constant you want, then the set of all points for which the slope function equals c is the isocline generated by c for the system. And we have a specialer name when c is 0. So in other words, the set of all points, you can almost think of this as critical points because it makes y prime 0. Right? The set of all points for when c is 0, or the isocline generated by 0, we call the nullcline. And just to get used to this vocab, let's do this example. Let's find nullclines to the logistic equation. Well, if you recall from a previous video, the logistic equation has the form dp dt equals, and I'm not going to go into all those fancy names for the constants I gave it before. It looks like p times a minus bp. So the nullcline is going to be whenever its slope function equals 0. Here, my derivative is already isolated, so I know that my slope function, it depends on p and, well, in a sense on t, though it's constant in t only. This is p times a minus bp, and the nullcline is going to be the set of all p comma t that make this equal to 0. So let's look. Well, that's a pretty simple algebraic equation to solve. My zero product property tells me either p is 0 or a minus bp is equal to 0. This solution we call the trivial solution because, well, of course, if I just put 0 in for p and t everywhere, of course, 0 equals 0. That's trivial. Over here, this is non-trivial, though. When I solve for p, I get that p is equal to a over b. So these guys are nullclines for the logistic equation. By the way, just a little bit of extra vocab, in particular when we're talking about ODEs, many people also call the nullclines equilibria or equilibrium solutions. And that terminology will actually make a little bit more sense here in just a second. So you may hear me use those words interchangeably. Okay, so if you recall, in the previous example, we saw that for the differential equation, dp dt equals p times a minus bp. We have equilibria, equilibrium solutions, nullclines, whatever you want to call them, but we have p equal to 0 and p equal to a over b were the nullclines for the system. Now, I want to pause for just a second and ignore the context that this is coming from a differential equation for just a minute. Notice this almost looks like, in this example anyway, a single variable equation if we forget for just a minute that p depends on t. And what you probably learned in Calc 1 is these would be critical points, if that were the case, for this function. And you can use the critical points to find where the function's increasing, decreasing, constant, find mins and maxes, all that good stuff. And that told you a whole lot of information about the function you're looking at. And we can give this differential equation the same treatment. So for right now, I want to imagine that p is not dependent on anything for just a minute. Let's do a quick refresher on what you might have done in Calc 1. You might have built a sign chart. Or perhaps your calculus teacher had a different name for it, where you would draw a number line, plot your critical points on the number line. If your function's continuous, which here it is, continuous in p, we would just pick a point let's say maybe -1, let's say half of a over b, and let's say twice a over b, for example. Right? We'd pick a point in each region to evaluate our function at, and here our function almost looks like a single variable function, right? F of p, and I'm going to put this in air quotes, right? I know p depends on t, but we're pretending, is p times a minus bp, right? So what I would do is I would check each of those points. When I plug in -1, and again, I don't really care what the value is per se. We have context from the logistic equation that a and b are positive numbers, so I have a negative times a plus b, which is a positive, right? I have negative a plus b, that's negative. I have that f of a over 2b, well, I'm going to get a over 2b times a minus a over 2, which is a over 2, that's positive. And then when I plug in twice a over b, I get twice a over b times a minus 2a, which is negative a. That's certainly negative. What does that tell us? It tells us that everywhere the derivative is negative, and remember, this is secretly the derivative of p with respect to t, right? That's what the slope function is. So what this sign chart tells us, if I've got positive in this region, excuse me, no I don't. If I have negative in this region, positive in the middle region, and negative in the right-hand region, this tells me that p is decreasing on negative infinity to 0, and also on a over b to infinity. And it tells me that p is increasing on 0 to a over b. Now we've got to stop pretending, though, if we're going to talk about phase portraits. P here really depends on t. P really depends on t. So let's draw the p t plane. Now what we just talked about was that p equals 0 and p equals a over b are nullclines, meaning it's 0 there. The idea of a phase portrait is it's really just a higher dimensional, in this case two-dimensional, sign chart. So the phase portrait works the exact same way as the sign chart in that we're going to test some points. It will tell us if we're positive or negative in those points. And then based on that, we can subsect the xy plane into regions where the slope is increasing, decreasing, all that good stuff. So we found that, remember, these are the functions of t. Really, this is p of t equals 0, and p of t equals a over b. So if I draw those guys in green over here, one of my equilibria, or one of my nullclines, is the t-axis. So here is p equals 0. And really that's p of t equals 0. The other is right here. Here is p of t equals a over b. So what this tells me is that in this region of the xy plane, any x comma y that, or excuse me, t comma p that falls on these two lines, in other words, if p are one of these guys, I get 0. And I know that my function p is continuous over the whole xy plane because it has to be if it's a solution to a first order ODE. So I kind of get that baked in, which is nice. So I have divided my region, or my xy plane, excuse me, into 3 regions, right? I have a region that I'll call A, B, and C. Let's check a point in each region. And again, I have the liberty to not just move left and right this time, but up and down as well. So for simplicity, I can check those same 3 points I did over here, It's just that this time I'm going to check them at t equals 0. So 0, -1, 0, a over 2b, 0, 2a over b. Notice I'm going to get all the same stuff because there were no explicit t's that show up in the right-hand side, right? When I evaluate my slope function that I now am not ignoring the fact it depends on t, or excuse me, I guess that's t comma p. Can't even read that. Oh well, whatever. When I evaluate it, I'm still going to get negative, positive, negative. It's going to tell me negative, positive, negative. Now, this means something a little bit more complicated for the system than increasing, decreasing. It is still true that the slope function itself is decreasing in regions C and A, and the slope function is increasing in B. If you think about the surface above this, that might be helpful to you. But I prefer to draw in 2D because it's a little bit more manageable. So how do I represent that in only 2D? Well, everywhere it's positive, I'm going to draw little up arrows. So I know in this whole region, regardless of where I am, I'm increasing. And the same thing is going to be true in... Oh, I need another color here. Shoot. Yellow it is. Same is true in region C, except I'm decreasing. Also in A. All right. Now the logistic equation has the solution, if I just take this general A minus B, P form, I get this solution, where here P naught is just the initial condition, whatever it happens to be. And what's so cool about this phase portrait is that I almost don't need to know that to infer this type of behavior about the solution. Two things as a quick aside. First, I'd recommend that you try figuring this out, or verifying that solution at least, on your own. It's a really good exercise. And second, see if you can throw that into a graphing calculator. Maybe pick a value of A and B if it helps. Maybe pick a value for P naught, see what you get. But now, let's look at the phase portrait. Do you remember that what we'll see a little bit later in our class is that the final solution to an IVP is entirely determined by its initial condition. And phase portraits are going to help reinforce that idea, or at least foreshadow it for us. Because the arrows on my diagram will help me to predict the trajectory of my solution just based on the initial condition. Here's how it works. If you give me an initial condition, let's say the population starts at A over 2b, for example, since I've already got that point here. The arrows tell me that since I'm in this region, I should be moving up. So I'm going to move up this way, but I can't cross the threshold here. Instead, I almost treat it like a horizontal asymptote. And I can follow that trend backward in time, even though it doesn't make sense to go backward in time for the context of a population or something. Same is true if I started at 2a over b, but here you'll notice that my trajectory should trend downward. So this time I'm going down toward the asymptote. Here, I don't have another asymptote or nullcline to worry about, so I can just keep going up and up. And then last but not least, if I were to start with a negative initial population, I know, kind of weird, but let's just, we've already used so much imagination today, let's use it a little bit more. We can see that I'm going to trend downward, and I don't have another nullcline down there to stop me, so I can just go off forever, but not in the negative direction. Here, I might trend toward that nullcline here, but notice I'm still decreasing the whole way out here. I'm still increasing in the whole red region. I'm still decreasing in all of region C. And this tells us some really cool info about the nullquines, or the significance of the nullquines, the equilibria, for the differential equation. And this is where that term equilibrium comes from. Do you notice any trajectory or any initial condition that I pick in region B or C will trend toward this nullquine? And because of that, we call it a stable equilibrium, or you may hear this called a sink in some contexts, depending on who you ask. The opposite effect happens here, where no matter which initial condition I pick on either side of this nullquine, my solutions always diverge from it. So we call this one unstable. Or a source is another term you might hear this called by. So if I think back to our tech startup company example, where we were tracking the number of daily users, what the phase portrait tells us is that it does not matter which initial population you start with. If you started with half of A over B or twice A over B, whichever you started with, since we can't actually have a negative number of daily users, right? So really it's just the top half of the phase plane here that I'm looking at. Regardless of how many users you start with, you should expect to trend toward this value, that there's a fixed population, in this case A over B. So in our previous example with the tech population, or excuse me, number of daily users for the tech company, right? We had that A was 10 to the minus 1, B was 10 to the minus 7. So this tells me that A over B, which is going to be 10 to the 6, or 1,000,000, is where our population trends to. Oh, well, of course it is. That's the carrying capacity. A over B is my carrying capacity. So that is the kind of information you can get out of the phase portrait.